Good afternoon to most of you, I guess. Good morning for others like me. It's a big pleasure for us to have Paola Inverardi here on this day. Paola is a professor at the Computer Science department at University of L'Aquila. She was a rector of University of L'Aquila from October 2013 to September 2019. Paola has researched quite extensively in the application of rigorous methods for software production in order to improve software quality. In the last decade, her research interests concentrated in the field of software architecture, and so it's one of the most appropriate researchers we could ever have here in our symposium. Not only on that, but also in mobile applications, adaptive autonomous systems, and quite a few other research topics. Paola has served in editorial boards of IEEE, ACM, Springer, and she has been general chair of leading conferences in software engineer like ASE, ICSE, ESSEC, FSE, and chair of some of these acknowledged conferences. And she's a member of the ACM Europe Council, and she's a vice chair of ACM European TPC. She's member of Academia Europea, and she's an Italian national delegate for the European Age 2020. Okay, I would like to, you can see that there's very extensive, achievement in her career. But some of the highlights I'd like to bring to you guys here is that Paola has received the honorary doctorate at Mälardalen University in Sweden, ranked as the 16th among the top 50 software engineering scholars in automatic and versatile publications ranking for research institutions and scholars. She has also received the honorary doctorate at Shibaura University in Tokyo, Japan. And in 2013, she received the IEEE TCSE Distinguished Service Award. Very impressive achievement. But also, I think for the community of the PhD students here who are going to present, it's really a life achievement for all the students that she has supervised. From 2002 to 2012, she supervised 12 PhD students, just to name a few: Henry Muccini, Marco Castaldi, Patrizio Pellizioni, Massimo Tivoli, Antonisca Di Marco, and Mauro Caporuscio, who's also here with us and part of the steering committee of Axiom. So just to name a few. So wow. So last but not least, Paola is an inspirer, not only from the research perspective, but she's also an incredible runner. She just told us that she does these days 10K per day. Wow, I don't even do 5K. Showing that doing good research and having a healthy lifestyle should keep up with the same pace. On top of that, Paola has an incredible and cheerful personality, tough when it must be though, right? Yes, without further delay, it's our utmost pleasure to welcome the keynote speaker of Axiom 2021, our doctoral symposium, Professor Paola Inverardi. Paola, it's a big pleasure to have you around. Thank you so much for accepting our invitation.
Grazie, Genaina, and I'm impressed by your presentation. I was saying, ooh, who is she talking?
It's your life. I mean, it's part of your life. You achieved them.
Okay, thank you very much. And I share my screen and see if I can start. And hopefully talk of a little bit of what I have understood so far in software architecture research. And maybe leave you with a few questions. Not sure about the answer. We will try to answer together, possibly. So why the title? The title is on the axiom of software architecture existence. So basically is is trying to demonstrate that software architecture exists, actually always existed, even if we ignored it for a long time. And they will always exist till, I don't know, I'm not sure. We'll leave the answer for the last question, okay? So, of course, I will go through a personal perspective. This is not because I want to advertise our own work, but it's because this is what I know better. And that it has been my way, my journey in this area. So, I will use it. But just an historical perspective, software architecture emerged, and I will say a little bit more, in the 90s, actually end of the 80s and 90s, as a potential research field per se. Then it developed in different ways. Basically, the first part of the development was about how you can specify architectures, which kind of analysis can you perform. In the next decade, it was about, exploiting this kind of abstraction. And then from 2014 on, my personal interest, it has been in looking at software architecture as the non-part of a system that you might want to assemble. We will see what I mean in a while. And eventually, at the very end, my current research is actually about what is our digital world today and how we can protect or, at least upgrade citizen users, normal, ordinary people, to a level in which their interaction with the digital systems that are surrounding us will actually, or could actually be or become a fair interaction. We will see it in a while. So, in my abstract, I just lay out a little bit of questions that I will try to answer. Again, I'm not sure I will answer, but so first of all, why has software architecture received attention so late? In the 90s. If we look at the emergence of software engineering is more or less, end of the 50s, 60s, and then it developed a lot in the decades after, in the last part of the 20th century, and which sounds funny to say because we were there, but it is like it is, and why we cannot ignore it anymore. This is a question that it's the opening question and will also be the end question. So the other question is, okay, but who is really interested in software architectures? Of course, there has been a lot of interest in the people who had or have a formal background, and we will see why. But at the same time, there has been a lot of interest also for practitioners, and I will, we will talk about this. So it's at the end, there is not a predominance, or if we can talk of a predominance, this will be on the side of the practitioners. So have we done everything? Do we know everything about software architecture? When I say about software architecture, I'm talking of software architecture in say, not the use of a software architecture in a new domain. Just in terms of what we have been developing in terms of, styles, kind of interaction protocols, properties that we can link to this kind of abstractions, things like that. And if not, what might be useful to research now? The other question that I will touch a little bit, it's but we have been working a lot in software architecture. Did we really exploit everything we did? or maybe something just remained there as a theoretical speculation. And if there is something which is still there as a theoretical speculation, is it still interesting? It is not, it's just junk. And the last question, which I think is the more intriguing one, at least for me, is software architecture just a natural abstraction for human developers? It's something that makes sense for us, but maybe if we look at, in perspective, at what we might imagine will be different ways of programming, is something that will make sense or not? Of course, I mean, it's a little bit rhetoric as a question, but it maybe it is useful to think about. So, I mean, first of all, what is our interest? Our object of interest is the software, as is. Software, in its more primitive form is a set of lines of code in a certain programming language that, when executed, produces a behavior. Of course, users are interested in such behavior. I mean, users are not interested in the software itself, are interested in the behavior. And there is the need, the universal need of trusting this behavior. So trusting means that we have to, be confident that the system we are using actually will deliver what we assume or we expect it to do. So this brings us to the other issue that it's a key issue, at least in my research vision, but not only in my research vision. Actually, everything we do around software engineering has this kind of target, which is dependability. Dependability in a very general setting, as it is defined by the IFIP working group on dependable computing and fault tolerance, is actually the trustworthiness of a computing system which allows the reliability to be justifiably placed on the service it delivers. Reliance to be justifiably placed on the service it delivers. So it's then dependability. You can split dependability in security, safety, availability, reliability. But it's what I like. It's this notion of trustworthiness that now it's very, very popular because of we talk about AI system, but actually it has always been there because it is exactly what we would like to do. Sorry, but I cannot go on. I don't know why. Let's see. Okay. How do we achieve dependability? Or what we know is that we do it all along the software life cycle, whatever it is, the software life cycle, from requirements to operation to maintenance. And usually what we do is that we analyze models of the software, we test the code of the software, and we monitor the execution. And more or less, we do it in circle, depending on the kind of software life cycle we are based on. Now, dependability then usually is obtained by analyzing models, and these models can be functional and non-functional, several abstraction levels. Usually there is not unique model. Through validation, and validation means normally testing. And testing, we have various kinds of testing: functional based, black box, operational based, white box. And again, we may use behavioral or stochastic models, either as oracles or as models that profile for example, the use patterns of the software. Monitoring execution, it's again implies looking at the software while it is running. And again, we are based on a certain model of what we would like to observe of the system when it works. We are not observing everything it does. We just, define what it is our interest to observe. And of course, it impacts on the middleware, on the runtime support that is used to run the system. So when we talk dependability, the focus is on both structure in terms of, the tool that can be used to make observations or abstractions, and behavior. So the models of slices of behaviors of the systems. So why I say that? Because, of course, I mean, when you talk about software architecture and you talk about validation, software architecture are just a view of a system. They are, again, a model, and you can apply everything I said so far to the software architecture level. But we cannot talk about the evolution of software architectures in these years, 30 years, without having in mind how also the software, the way we build software has been changing. It should be clear why we are saying that. I mean, if we look at an abstraction, because it is useful to, increase our trustworthiness in the system, then we might want to make proofs, and then these proofs go, hand in hand with the way the software is developed. So it's useful just to keep in mind how this way of developing software has been changing. So 60s, the birth of software engineering. So first, attempt to understand methods and complexity and problems, of course. The 80s are the decades of the software processes. I mean, before there was just the streamline. Streamline. Software process, but now then there was a lot of discussion on different ways of organizing the different phases of software development. The 90s is the decade of software architecture, as we will see in a moment, a specific phase, to some extent ignored till that point. The year 2000s, it's the year of component-based software engineering, a complete shift of paradigm from top-down development to bottom-up development, completely bottom-up development. I mean, components off the shelf and the ability to put them together, I mean, standardized interfaces, and then, the vision of being able to build software like hardware was actually composed. 5 years later, very, very soon indeed, there was the emergence of service-based software engineering. Service-based is again another shift of paradigm. So no more standardized code that we can take off the shelf and assemble on our site, on our machine, and run it, but just, ask for a service. And the service is a dynamic object. You call the service and he runs wherever it is and will deliver what it is supposed to deliver. But again, services come with an architecture and come with a way of assembling services together to build more complex services. And then the app market, and then to some extent what we see now, it's just an evolution of the last two paradigms. Just app and services, and you mix things together. So more and more we have been moving from a top-down world to a bottom-up assembling world. So what I call is the beauty and the beast, and this is my personal story, to some extent. So this is a piece of software. I have never been, attracted by software itself. It's quite boring. It doesn't mean anything. And actually here, we are already working with, an excerpt of a program that it's quite understandable. But software itself is definitely not something that appeals, at least to me. So this is our beast, and it's complex. If you have to go through, hundreds or thousands, or I'm not talking about million because it's beyond human possibility, lines of code is not exactly what you would like to do. So, I mean, this is the beast on my... But how can we trust the beast? I mean, trusting the beast is difficult because you have to make a sense of all these, lines of code. And what I was suggesting, and if you have you look at it with the bell eyes, then maybe you can make a sense of what's going on. And just make an abstraction step and try to, look at this piece of code as indeed, a more abstract components that actually can interact. So this is what I call the Bell's view. I mean, of course, I liked it much more than code itself. So I mean, so software architecture was something that actually was appealing. Why it was appealing? Let me tell you why it was appealing compared to something else. I mean, it was appealing because it was giving a view of the code, of the structure of the code, that was embedding also, to some extent, the behavior. So you could, at one time, get a sense of the structure, of the syntactic structure of the code, but also of its dynamic behavior. And this was much more, useful, at least on my side. Just let me tell you a little story. When I started working on software architecture, actually I was working with Alex Wolf, that I met at a configuration conference, configuration management conference. So then we talk also that. And he started, and he came to visit and said, okay, we are in the United States starting working on this stuff that is software architecture. And they said, what is software architecture? Come on, software architecture is the structure of the code. And then I was thinking, but who cares of the structure of the code? I was more on the specification side. So why shall I bother about the structure of the code? And it took to me a little bit, to just make a sense that actually this abstraction of the code, that for me was the implementation. I had the view of implementation, like a black box, it does something, then we test it and poof, something happens. And instead, at a certain point, I started seeing this mass of line of codes in a different way, with the eye of Bell, and said, maybe we can make a sense of it. And maybe this can ease the validation phase, can actually help us in validating it better. And actually, this is what it was. Of course, you can then provide different models or abstractions of your architectures, and through these models, different models, depending on which kind of analysis you would like to do, you could actually prove something. So and then I close, and I will go very much quicker than that. I just give you a free excerpt of 3 basic papers on software architecture. Look at the first one that I'm mentioning is Mary Shaw. Larger scale systems require higher level abstraction. This is IWSSD 89. So this was the International Workshop on Software Design, Specification and Design. So the objective was specification and design of the workshop. And Mary there had a short paper that was saying basically, okay, large-scale systems involve design at a level above the traditional module. At this design level, the objects of interest are subsystems and their interactions, rather than data structures and algorithms. Support for design at this level requires systematic identification and analysis of useful system organization and the components from which they are constructed. So, I mean, it was, the very beginning in which there was the need, or at least it was highlighted, the need of expressing these high-level design concepts that were there. They existed. They were in the software. But researchers, software engineers were not able to refer to this abstraction. Then there was another paper in the same proceedings by Robert Schwank and his colleagues. These were people from Siemens at the time, a Siemens research lab. Of course, these were researchers, definitely, although working for Siemens. And in this short paper, they were talking of software architecture as a way to bridge the gap between software design and software maintenance. And they were actually proposing a tool that they were developing at Siemens Research that had a sub-project called Arch, that it was developing a new approach to controlling the structure of a large software system during maintenance. The approach assumes that a large body of code may already exist before the structure is formally specified. Where the point here is that software architectures existed. They didn't exist in the mind of a developer at the very beginning as a way to help the development, but they did exist in the code at the end, because it was a natural way of managing complexity of the implementation. And then in 92, but actually, I mean, the paper was actually prepared much earlier, around the same years, in 89, 90. There was this paper by Perry and Wolf, Foundations of the Study of Software Architecture, where they were making this similarity with architecting buildings, architecting softwares like architecting buildings. But what I think is more interesting, apart the similarity and what they discussed, is this last paragraph that says some of the benefits we expect to gain from the emergence of software architecture as a major discipline are architecture as the framework for satisfying requirements. This was, something expected, okay, I can actually perform a first step of validation of the requirements on the high-level design. Architecture as the technical basis for design and as the managerial basis for cost estimation and process management, and also this was very much exploited in the year later on. And third, architecture as an effective basis for use, and again we will see this is actually what is going on now and from COTS on. And fourth, architecture as the basis for dependency and consistency analysis. And this is what actually people in analysis like me and other people were doing. So just to give you an example, exactly in the same years, don't look at the publication years that of course were something that came a year after the research was developed. We were working in Europe on large system built with the language that at that time was actually offering primitives for structuring big software systems. In particular, we were working with Ada, and we were working with the Ada configuration primitives. So basically, we were having a programming language approach at the high-level design that for us at that point was configuration management. Now, what happened a little bit later on? There was a lot of work on analysis and specification and languages. First, specification formalism and analysis, and then architectural languages. So here I think you all know, but it's better to remind us that there was Rob Allen and David Garland, and they proposed, the Allen, and actually what they proposed was this notion, formalize this notion of connector. And connector is actually a component. There was a long debate about is connector a component, is not a component, but who cares? I mean, it was an abstraction that was trying to, separate concern, the interaction concern, from the computational concern of the component. So, and the notion of connector was then much exploited. We were also working on this area, and we were using another formalist, was the chemical abstract machine, and we were performing several kind of analysis on specification of software architecture. Up to this point, we were not doing things very different from what people in specification were doing, except that we were focusing on an abstraction of the code, while people in specifications were focusing on a way to model typically requirements. We were then interested in understanding, okay, but can we exploit software architecture for helping the real validation phase? So for helping testing. And actually we worked a lot on that. It was Henry Muccini's PhD thesis. And what we did was actually try to exploit the specification of a software architecture to drive the testing strategies in selecting suitable test cases. Just to mention, I mean, this was quite a theoretical paper at the end, although with a certain degree of methodological proposals. And just mention that actually this paper has 2 patent citations. So this means that even if we didn't actually come up with a tool, because it was impossible to automate the test selection and so on and so forth in general, without looking at it was more a methodological strategy, then there have been people who actually were inspired practically and in practical proposal, of course, of more limited context. So the other kind of effort what we did in terms of analysis, and it was not only our effort, was in trying to understand if it was possible to exploit software architectures as a specification for proving quantitative properties of a software. Actually, not of the software, because the software it's going to be developed, but of different high-level design. So useful to compare. Sorry, I just went to one here. Different software architecture. Different software architecture that could actually exploit already, could actually made visible already potential performance problems. This was a line of work that we tried also to couple with the line of work that was going on in software performance, which was actually targeted to attach to a software system, so to the code, a performance model in order to evaluate the performance of the code. And it was very interesting and actually very promising, and with a lot of potential exploitation. And actually, from this point of view of the quantitative and more dependable properties, there have been then tools that not on our side, but I just mentioned Palladio and other tools that were actually coming out of, I will show it in a moment, from research at universities. We worked on also a framework to analyze functional properties And this was Patrizio Pelliccione's PhD thesis, and tools that could actually help the specification and analysis. And beside us, there were many other tools, and actually now there are tools that can help you in analyzing the dynamics of your software architecture model. Oops. Okay. So far, what was the software process? I mean, again, we were in a here I mixed up the two slides. So we were in a top-down setting, more or less. We had a very large system, so it's not what is written here. And the main issue was proving consistency between requirements and design, and then exploiting the first model checking tools and performance analysis. But we were in a basically top-down strategy of development. Later, in the years 2000, instead, we started working on bottom-up ways of producing software according to the COTS paradigm, and later on to the service paradigm. And there, actually, the software architecture played a key role, because it played the role of what we knew. I mean, in a COTS environment, you were acquiring COTS. You didn't know anything. I mean, you just knew the interface and the description of the dynamics. So one of the typical problems that people had was putting things together and then having behavioral problems like deadlocks. So this work was instead basing on a software architecture, so a way to put things together and exploiting the knowledge of the software architecture in terms of what we expected from the components and how the interactions were going on. We could actually produce in an automatic way glue code that could prevent dynamic problems like deadlock. It looks a little bit magic, but it is not. So there, we had a component-based software process, very large systems, bottom-up, we were all reuse. We had these behavioral mismatches. And the main issue here was to prove that the assembled system does not have dynamic problems. It does not deadlock, but then you can also go beyond deadlock and actually show that has some kind of nice property. And this was exploited was exploited then in the work that we did in service-based systems, where we were playing more or less the same game. At this point, the service-oriented paradigm was known, so that was the architecture. It was known the way services were called and could interact with the rest of the system. This was also usually you were assembling services through choreographies, and then we have been able to exploit all the knowledge that we had in the component-based setting to actually produce glue code and that could make the choreography, as it is said, realizable. That means that there is an implementation that actually can put things together according to the choreography as specified and does not create dynamic problems. I go fast here. This was done for BPM MN2, and now this is a tool and it works to So it has been actually practically exploited. Now, going on, we were facing another kind of problem. And this is what I call the integration architecture for the open globe. So we were working in a project, a European project, very visionary project, but actually we put together with Valérie Sarny. And the idea, the vision of the project was, okay, we live in a world in which we have all these systems going around. We would like to produce tools that can allow systems to meet, to come together, to interact, produce other things, and then maybe disappear. So the key issue here was that we had systems, component worker systems, how we call them, that could be very different, although sharing the same purpose. So they could exhibit different protocols, both syntactically and semantically. It means that also in terms of the semantics of interaction protocol could have been different. And then we were able, through a synthesis process, to actually produce what we called the mediator or adapter connector that could actually allow this connected system to work together correctly. So again, here, the only way to cope with a problem that had to do with unknown systems that we do not own, and then we cannot operate on them, we can just put them together, but we can create something in the middle that can actually allow them to cooperate. So, real mediators. And here, the whole approach was architectural. So the whole approach was based on building an architecture that could actually make possible what I described. So this is a very simple example of two systems that actually P and Q that have the same intent to some extent, but different protocols that you can see here. And what we were able to do, I mean, you cannot just let them interact because they would not be able to interact. What we were able to do through a set of processes and tools to actually find a way to find a common layer, if possible, and then build the communication mediator. The last part of my research is in a completely different now, is in the present setting. The present setting is what I call the architecture for trustworthy digital world, a Mr. D. So here we are surrounded by autonomous systems that interact with us, users, and these systems may often go beyond the boundaries that of their own functionality, and you know, steal or invade part of the prerogatives of a user. The talk I was attending today was exactly on how we can regulate AI potential risks and dangers with respect to the basic values of a human being. So, I mean, the setting is this one, and again, the approach that we have is, I mean, how can we protect the user then? I mean, the idea then is to see the user as one component that interacts in the digital world with all the possible other systems, and then the approach is to empower the user with a software exoskeleton, we call so pieces of software that can mediate the interaction with the different digital systems that the user with that the user interact. by guaranteeing that the moral preferences and the characteristics of the user are protected. So this is obviously an architectural approach. So we have this exoskeleton, but it's a mediator attached to the user that is able to interact with the system. I cannot go on the detail, but I mean, the point is that at the end, the user with her own software can actually be able to interact in a better way with the digital world. Now, after this very quick excursus, I mean, let's say, can we look again at the question, no? So why did SA receive attention so late and why cannot it be ignored anymore? I mean, now, this should be clear now. Software architecture existed, they were there. Simply, they went unnoticed till the point in which actually they made a difference in terms of conveying more information on large, complex software. So, for example, it became more and more popular when the software architecture issue came up. To read in the description of real system, I mean, the system does this and that, the system is based on a client service architecture. So actually, the information was there and it came up. So the architecture was there, and at a certain point, it went uncovered. So why cannot be ignored anymore? This should be clear now. We move more and more towards a world in which we have to cope with putting things together. And this putting things together is dynamic. So there are interactions. And this is architecture. There is no way. This happens for IoT, it happens for cyber-physical systems, it happens for us humans, it happens everywhere. So they exist. No way. It's our way. And if you reflect about it, it's actually the way people go together. So it's for foundationalist or practitioner. We have a little bit answered here. I made reference to Palladio, for example. There is also this Axiom company that comes from research efforts in university, but now it's it's solid. And I just refer to this just to say that, okay, some of our own research went to the practice beyond what we know, UML, the tools, and the Software Engineering Institute, all these things we know, but there is more. Actually, some of what we did went on the market and was used. Is there anything new to uncover? Yes, there is a lot. For example, we are not... We were not able, and we are not still able to attach to a given architectural style a set of property. And this should be relatively easily to do. And at least there is the intuition of this could be exploited better. So we were not able to really work properly on this pattern or architectural styles by actually attaching to the pattern something more relevant, like properties that can be automatically guaranteed or automatically proved somehow. Did we bring to practice or we discovered? No, we didn't. And we could do more, probably. Especially in the area of analysis, we were probably much more sophisticated at the research level than actually we were able to bring to the practice. Are these results still of interest? Yes, they are. Surely they are. They are, especially because we can bring them to the new development paradigms, and then we can actually exploit them much better. Now, is SA just a natural abstraction for human developers? What do you think? Of course it is, no? But if we imagine that, I mean, not imagining that we will not have software anymore in the way we have been able to see it, no? I mean, just if you think of quantum computing, but not going that far. Just thinking that we could actually exploit a little bit more of automated repair or automated development just by, pushing more on this data-driven development, then would really be useful, the software architecture, or software architecture is something for us, which actually we have been using for our mind, but not something useful. I don't know. I mean, just leave this here. Now, this is, Genaina was telling it, no? So, I mean, these are my 15 PhD students, and I'm very proud of them. But this is, because this is a PhD symposium, I just would like to convey the information that it, it might be convenient to work on software architecture. It's not that bad. So, I mean, the one in blue are all in the academic career, with different roles so far, but all of them are, and the other ones are in very, very successful careers in very, very important places. Just mention that Fabio Mancinelli is it's at the intelligent cloud control at Amazon, so actually dealing with autonomous large complex systems. Okay. Many other colleagues, of course, I mentioned here only a few of them, and that's it. I think I can end, and I can stop share. Thank you. Hopefully on time, Hopefully, yeah.
Oh, speechless, Paola. So we now have, we can say 19 minutes for questions. So we still keep the break for 15 minutes, and I'm sure that that will be plenty of interesting questions coming out here from the audience, given the very broad and at the same time inspiring talk that our keynote speaker had just given to us. So who wants to raise the first question, please open your microphone and post your question. Rado, there you go.
Right, sorry, I'm not sure if it's fair for me to start, but I'll start anyway. So Paola, thank you for the very interesting keynote talk. You already mentioned AI and its growing importance, but I was wondering if you can tell us more about your view on the impact of machine learning and AI on software architecture. Will we be able to include ML components, AI components, you think, into software systems in a similar way in which we integrate traditional software components?
Yeah, actually, thank you, Rado. Actually, this is something that was, I said it, I mean, it was there, but I didn't say it. But yeah, I think that the way we can cope with software engineering for AI systems, mentioning with AI systems, software systems that include AI components, is actually an architectural approach. There is no other way to me. And I didn't mention, because I didn't work too much on that side, but there has been a little bit, quite a lot of work on software architecture for reliability, or fault assurance and so on. It's natural, but the approach might be to encapsulate to somehow, to encapsulate your component and try to filter out behaviors that you might not want to have. However, the point is that, this has to be coupled with a little bit of explainable AI. I mean, you need to know something about your component. It cannot be just, something unpredictable. You need at least to understand if the behavior that it exhibits is more or less deviating from what you expect. And then if this is the case, I mean, you can, from an architectural point of view, cope with it and try to not, you know, to not break your system, the old system. So definitely I think that the approach is architectural, but it has to be coupled with, you know, the people who do explainability. And the nice research issue here might be to tell them which kind of explanation we would like to have, depending on the way we are integrating the component. So what is what we might want to, no, them to look at, not just everything, no? It's so
Can
this
we
is
have a service level agreement? Can we have a service level agreement for a ML component or AI component?
Yeah, service if it is service, but of course it might be even trying to understand deviations or not. So you might want to have information about you know, frequency of answer of a certain kind. I don't know. It depends on the context, no? But yes, definitely. I think I would imagine that this is what we have to do. On the other hand, as I was discussing with in a panel at ESEC, FSE, a few weeks ago, with Paolo Tonella, that was actually saying, you know, validating AI system is difficult, machine learning, no, neural networks. And then I said, okay, but I mean, as software engineers, we have been working with potential faulty components. So as long as we can, to some extent, you know, define some interface information, we should be able to cope with that. It's not different from having an hardware component, no? Except that for hardware component, we know that we can have a reliability profile or so. Okay, we should work on that direction. But it's very interesting.
No, thank you for the positive answer. I think when we, I guess, buying off-the-shelf artificial eyes, have a pair of eyes and incorporate them into a system. Thank you very much, Paul.
Okay, so if anybody has a question, I do have one. So I'll give the priority here to the audience. Okay, so I will pose mine. Okay, sorry. Okay, go please.
So, yes, this is Felicien. And I think I'm just having a curious question, or maybe somehow need a clear clarification from Paolo. So the software architecture seems to be, I'm trying to understand where this model-based software engineering fits into software architecture ecosystem. So maybe you know very well, and you can tell me that, okay, model-driven is something which is here in software architecture or is out of software architecture. Thank you.
I don't know if I have well understood your question, so please correct me if I'm not. But you know, what is modern software engineer? I don't know. What I'm thinking is that we, in my historical perspective, we moved from a software world in which we were actually operating in a sort of closed world where we knew everything, potentially. No, everything was clear. It was specified, bad or good, but it was specified. Moving during the year in instead obtaining systems that have more and more parts that are unknown, for which we cannot know anything or know a little. And now we are to imagine now you build a system taking and putting together services of which you don't know anything. You just know the little bit that you want to use, but you don't know anything else. No? I mean, just assembling Amazon services or Google or whatever. Huh? What do you know about those systems or these services? Do you know, what do you know? We were not used at that. We were used, at integrating things that we knew, or at least potentially we knew. Here we don't. And we go more and more in that direction. So actually what you really have in your hand is the way you put things together. That's the only thing that you have. Even when you plug things together, you have a possibility to add pieces of code. And that's what you own. And this is entirely an issue, an architectural issue. It's only architecture. So that's the role in my vision. So actually what you do when you build a system now, integrating things, it's building an architecture.
Okay, thank you.
Good. Anybody would like to raise a question? All right. Okay, so I'll take my opportunity here. Oh, sorry. Okay. Colin Venters, please go ahead.
Sorry, I was waiting to make sure that none of the PhD students weren't going to ask a question. So I'm not a PhD student. I'm just a general participant at the conference. Great keynote for the PhD students. A really nice overview of some interesting stuff. You mentioned the Q word, the quantum. What do you think the future directions for software architecture are in the quantum computing field? Or
no, I don't know. I don't know at all. I mean, actually, I know very little about what's going on in although I should know because I'm working. But I know very little. I mean, but I'm just mentioning it because it's a change of paradigm. You know, we lived in the world of von Neumann machines. That's it. No, I mean, we are working with programming languages that are von Neumann programming languages. No, so I mean, that's basically that. So what it will be working with a completely different computational paradigm, I don't know, but I imagine it will be different. So I cannot answer. But I was just. But even not going that far. No, as I was mentioning, just thinking of exploiting. I'm not a fan of data-driven approaches, but at the end, we would certainly expect that. We will be able to just automate the development of portions and portions of software by just exploiting machine learning techniques on existing repository. No, so that's I think that's will be possible. And then at that point, will software architecture be a useful abstractions? Maybe yes, maybe no. I mean, there should be a human at a certain point. If there is a human, I think, yes. Basically, my question was that I think that it's a human abstraction. Because we are not machine and we need abstractions and we need to divide things and to understand and make them less complex, no? But it's a human activity. So if a human goes out, I don't know. But maybe not, who knows?
Okay, so just checking here our time. Right, so we still have another 8 minutes to go. So can I, if you mind, if I...
Janina, there's a question from Ron.
Okay, sorry, I didn't see that. Okay, so those that want to ask questions, please raise your questions, raise your hands, and we can see from the queue here, okay, the order of the questions, okay? So now it's Rod, please go ahead.
I have a couple, one following up Colin's question and Paula's answer. I tend to agree on the human abstraction, like thought of it, but then I was thinking as you were explaining the machine learning process of kind of like choosing the right like architectural candidate or whatever, that even if you don't have like a human involved, you still have to choose like the correct combination or permutation of components to have like the proper solution, right? So at that point, do we still need the human in, like, even if we don't have the human in the solution, there's still the problem of choosing the right architecture, right? So it stops being a human abstraction to being kind of like the goal of fulfilling, going back to fulfill like the concerns of the stakeholders, right?
Yeah. You're right. Yeah, of course you can think that you can automate also this. No, I mean you have a library of architectures or patterns and things like that, and then you just run your system. But your machine learning algorithm. I mean, I'm just thinking that it might be, but you do not need it, unless for maybe explainability reasons for a user who looks at the code afterwards.
Okay.
But it's difficult to say. I mean, it's I put it like a question. I don't know really. No, maybe it's too early to say. It's
no, it's super interesting. No, my original question was like, it was pretty interesting how you divided like the software architecture like in phases. And I've been pretty into like studying and going into the functional specification back like to the end of the late 90s and stuff like that. And one of the thoughts that I currently have is like, does it make sense to go back to that phase now that the software development cycles, processes, technologies, having the cloud, having machine learning, like, is there value in going back to revisit all those different papers, proposal, languages, and specifications, like with a different view, like from without a current context, or is there, or it maybe doesn't make sense because whatever was proposed is still like applies today?
I don't know, maybe revise not, but just look with fresh eyes at the new possibilities, yes. So not being biased to some extent.
Okay.
No, so I mean now you have different tools, but you need also different abstractions then. It depends, no? I mean, again, what are your data? If your data reflect our conventional way of thinking, then I mean, even the search and even the the way you teach your learning algorithms will reflect that. But if we look at it in a different way, then and we have data represented differently, then it might be.
But I think in this one, I wasn't going for the machine learning one. I was going more generally, like, does it make sense? Because we have had like so many different architectural languages, so many different tools. And my biggest, like, I'm from the industry, I work for Amazon. So my biggest usually wow is like how much things we have developed in the academia that is not used in the industry. So I'm trying to look into that. So one of the things that I'm thinking is like, maybe when things were specified back in the 90s, like by Wolf and by like David and all those authors, maybe the industry wasn't prepared for like a lot of things that were proposed back then, or maybe we didn't have the tools, or we like, because it's different what we used to have back in the 90s to what we have right now in terms of natural language processing, the cloud, microservices. So my question was towards that, like, does it make sense, for example, and given that this is like a symposium, as a student, to go back to those foundational papers and try to see what makes, if anything, makes more sense now than back in the day?
I mean, this is always useful. My impression is that it is not. But because again, as I try to explain, I mean, as often happens, it was an a posteriori problem. So software architectures existed, were there. I mean, people were actually building in the system of software architecture, and then it was a sort of a reverse engineering effort, not even trying to establish, languages or concepts, but it's always useful anyhow. I mean, that's so. Let me put it this way: if the hypothesis is what I said, that software architectures already existed, and actually at a certain point we're trying to understand how to conceptualize what already existed, in order to exploit it better, then this means that this was already there as practice, So it reflected something that was there, and might not reflect the way people might do development if other tools are available in the future. You know what I mean? So it's
Yeah, that does make sense. Thank you.
you know, there is a bias to some extent. Now, this is again is the bias of also machine learning and data-driven stuff, no? Because I mean, you know, when just let me say something about it because I think it's truly true. No, I mean, something is you know, training a machine to recognize a cat, showing a picture of a cat that exists in nature, and it's a cat. Something else is training a machine on a human being artifact, which by nature is changeable and depends on, and it reflects the culture, the knowledge, the technology, in terms of even of knowledge, that the people had at that time. You know what I mean? It's like a bias. It's a technical bias. It's not an ethical bias, but it's a technical bias. So for example, now I'm working on privacy. Training your machine learning tool on the way people have been setting their rights, no, their settings, no, for privacy in the past might not reflect at all what people will do in the future.
Mm-hmm.
Because the awareness of privacy that there is now, there was not 10 years ago, there was not 3 years ago. You know what I mean? I mean, it's very sensitive as a topic, this one. But very interesting, by the way. So.
Okay. So, Paola, we are approaching the end. I'm not sure if we still have time for further questions. So, or maybe we can just be informal here and then maybe can close the session so people can have a 15 minutes break. So
Sure.
maybe it's better to approach the end. But I would still like to have one during the break, quick discussion with you, something that's spotted here on my mind. But anyway, let's give a big applause to Paola for this fantastic time that she has given to all of us and sharing all these, let's say, great axiomatic knowledge with us. And it's really, really big pleasure. Thank you so much, Paola. Grazie mille per tutti.
Grazie a voi.
Grazie.